The third section of the chapter looks at fluids, so gases and liquids, and we're going to look at how those behave. So first of all fluids create pressure. If we think about what pressure is a force applied over some area. So how do fluids exert a pressure? Well, they exert a pressure by pushing on their container, and they do that evenly in all directions. Pressure is defined as the amount of force exerted per unit area of a surface. Okay, that sounds hard, but really all that means is that when you put air in your bicycle tire, for example, the air particles are bouncing off of each other and bouncing off of the tire, and that is applying a force. And if we find out how much force that is, and we divide by the area over which the force is being applied, then we have found the pressure. So we end up with an equation, P is equal to F over A. If we need that to be in triangle form, our F is on the top and P times A is on the bottom. The SI unit for measuring pressure is the Pascal. Technically, it is newtons per square meter, but in order to honor Blaise Pascal, who worked with gases, they gave it its own unit called the Pascal. We symbolize that with a PA. So force then is measured in newtons and area is measured in square meters. Now, those forces, depending on what we're talking about, can be very important. So if we think about why a rubber duck is able to float in the bathtub, it's because whatever fluid is in it is providing an upward force that we call a buoyant force. All fluids provide a buoyant force on objects that are immersed or floating on that fluid. So buoyant forces are the upward forces that keep an object immersed in or floating on a fluid. And it was Archimedes who is the one who first used the idea of buoyant force. The story has to do with him being asked by the king to find out if gold was being stolen out of his crown and replaced with a different metal. So Archimedes had to figure out how he was going to find the density of the gold crown, and because the crown is such an odd shape, he had to figure out how he was going to find the volume of such an oddly shaped object. So it's said that one day when he was trying to think about this, he headed to the baths in ancient Greece, and when he stepped in the water and he noticed the water level go up, he realized how he was going to find the volume of that odd object. He was going to use water displacement, and apparently because he was so excited, he ran through the streets naked, screaming, "Eureka, Eureka, I found it." So Archimedes came up with the idea of using water displacement to find out how much force is being applied to an object. He says that the buoyant force on an object in a fluid is an upward force that's actually equal to the weight of the fluid that the object has displaced. So how do we do that? Well, Archimedes would use a special tool like this. If you set up a beaker that is full of water up to the little side vent here, when you lower an object into that water, obviously the water level goes up and it causes some of that water to travel down through that side vent. And if we capture that in another beaker, we can find the mass of the water that has been displaced by putting that object in the container. If you compare the weight of the fluid that is displaced to the weight of the object, you're able to find out how much buoyant force is being applied. So, comparing the buoyant force to the weight actually will tell us whether something would float or sink. If the buoyant force is equal to the weight of the object, then the object is able to stay suspended. There's not one force that's greater than the other, so the object is able to stay in place. Fish do this by changing the amount of air that's in their swim bladder. If we instead look over here at the shell, the weight of the shell is a downward force that is greater than the buoyant force or the upward force that is acting because of the water. So that means that the shell will sink to the bottom. If we look at the bird up here, the seagull is only partially in the water, so it doesn't displace as much water as it could if we push that seagull underwater. Not that you should do that, I guess. But if we compare the downward force of the entire weight of the seagull that's sitting in the water compared to the weight of the water that its lower body and legs have displaced, we find out that they are the same, and that means that that seagull is able to continue to float on the surface. I think from past that you also know that density plays a role in whether something will float or sink. If an object is less dense than the fluid, that means that it will float. If an object is more dense than the fluid, that means it will sink. So how do we take advantage of that? Well, we can take something like a large piece of steel that truly is more dense than water when it is in a block, because its large mass is a small volume. We have a high density. But if we take that block of steel and we stretch it out, make it flat, and then introduce this curved shape like the bottom of a ship, we have significantly increased its volume without changing its mass. Now the mass to volume ratio is lower than the density of the water, and the ship is able to float. That's how we get large ships to float. But it's very, very important that they're careful about how much mass is added to the ship, because if you add too much mass to the top, all of a sudden it can throw off your density, and you can make it possible for a ship like that to sink. Along with Archimedes' principle, we can look at Pascal's principle. Pascal's principle has to do with pressure on a fluid and what happens when it changes. So it says that a change in pressure at any point in an enclosed fluid is transmitted equally to all parts of the fluid. In other words, if the pressure in a container is increased at any point, the pressure increases at all points by the same amount. So the pressure is equal to the pressure. That's kind of weird mathematically, but it really comes in handy because pressure is force over area. So the initial force over the initial area will equal the initial or the new force over the new area. We put that to work in hydraulics. So if you take a look at this diagram, hydraulics essentially put an enclosed fluid into a setup where we have a small area connected by a tube to a much larger area. And then at the top of each of these two tubes, we have what are called pistons, and they are movable. So now, if we apply a downward force on this side, that force is transmitted throughout the entire fluid, and it generates an upward force over here. Now, that doesn't seem all that impressive. That seems pretty obvious. But what's really cool is that since the pressure has to stay constant throughout, we have a small area attached to a large area. And for our ratio to stay the same, that means that we can only apply a small force here, but with our large area, we can get a large force over here. So how do we do this? Well, let's apply this to a problem. If a hydraulic lift is going to be used to lift a 19,000 Newton car, and the small piston has an area of 10.5 square centimeters, and the large piston has an area of 400 centimeters, we can find the force that we need to exert on the small piston to lift that car. So we know our out force, or our new force, is going to be 19,000 newtons. Our initial area, area 1, is 10.5, and our area 2 is 400. So if we set up our basic equation as a ratio like this, force 1 over area 1 is equal to force 2 over area 2, we can then cross multiply and divide, and then we can substitute in our known values. So our force 2 is 19,000 newtons times our area 1, which is 10.5 square centimeters, divided by our area 2, which is 400, and which is 500 newtons of force, we're able to lift that 19,000 Newton car. When fluids move, other things begin to happen. Fluids actually move faster when they are forced through a small area than they are moving when they are going through a large area. You probably have done this yourself with a hose. If the water is coming out of the hose too slowly and you want it to come out faster, you use your thumb and cover the end of the hose, making a smaller area, which means the fluid then moves faster as it comes out of the hose. This is true on rivers as well. Water moves very fast through the smaller, narrower parts of a river than it does through the larger parts of the river. Viscosity is something that you may have heard of. Viscosity is the resistance to flow. Essentially, you can think of it as how fast or slow something will move based on particle attraction. So particles that are highly attracted to each other move more slowly than particles that are less attracted to each other. Fluid pressure decreases as speed increases is actually Bernoulli's principle. So if we have a change in speed, then we can also have a change in pressure. The faster that a fluid is moving, the less pressure that it actually generates. Bernoulli's principle is the reason that airplanes fly. We shape a wing on an airplane so that the air moves fast over the top and slow under the wing, which means that we have high pressure under the wing, low pressure above the wing, and that's what generates the lift on the airplane.